Hi, welcome to the video solution for Edexcel Physics past paper. This is Edexcel Physics IAL, new specification unit 2, October 2019. So let's start. Question number 1. The resistance of some electrical component decreases as the applied potential differences increases. Which row of the table contain two components that behave in this way? So if you see, they are saying resistance resistance is changing, or in fact decreasing when voltage is increased. So we have two components that behaves in this way. First of all, remember, whenever you find the word ohmic conductor, so ohmic conductor is the conductor that does not change its resistance, or its resistance stays the same. So option A and option B are immediately gone. Don't waste time to think about these options. So the number one is a negative temperature coefficient thermistor and diode, and negative temperature coefficient and filament lamp. So the first column gives you negative temperature coefficient thermistor. Yes, if you increase the voltage, then resistance decreases because amount of current increases. So from first column we cannot select C and D, but if you see D, what is happening here? It is filament lamp. If you increase the voltage of filament lamp, then resistance also increases. So but they are saying the component that behaves in the way that resistance should be decreased with increase the potential difference. So of course this is diode. So remember, it's and these are the two component in your specification that behave, or that we discuss in this way: thermistor and the diode. If you increase the voltage, then resistance of these two component decreases, so the amount of current increases. It is because of increase in number of electrons or charge carrier. That's how you define. So your option is C. Question number 2. The circuit shows a resistor of resistance R connected to a cell of EMF E and internal resistance R. When the current in the circuit is I, the terminal potential difference is V. Which of the following is an expression for the power P dissipated in the internal resistance of the cell? So if you see, you need to find power dissipated in internal resistance, which is this R. That means if you need to find the power dissipated in this internal resistance of a power, generally we find P is equal to VI, or P is equal to V square over R. It's a general approach. R is the resistance of a component, and P is equal to I square into R. This R is just a resistance of the circuit or the component, and it's all about, EMF, internal resistance. One equation that relate EMF and the voltage. So this whole circuit describe that current I is flowing through the circuit. This is R, and the voltage across this external resistance is V, and this V is called terminal potential difference. Remember, terminal potential difference, which is this. So this V is across R, or maybe you can see this is the terminal potential difference across the power supply till here. This is V. So we have a relation between E and V, and you can say that E is equal to V plus IR. This is the relation between EMF and the voltage, or terminal potential difference, where IR is voltage drop or lost volt in R. So this is the lost volt due to internal resistance. In fact, in other way you can say this is voltage across internal resistance. Voltage of internal resistance. That means if you say this is a small resistance or internal resistance, so across this internal resistance we have a voltage VR, and this VR, remember, equal to IR. So we can write this equation as E is equal to V plus VR, and clearly it is according to the condition sum of these two voltage V plus VR should be equal to EMF, and VR, voltage of the internal resistance, would be equal to E minus V. Now we can use the first approach to find the power dissipated around internal resistance. So you can say that I is the current flowing through the circuit, and V is the voltage of the component, and here component is R, internal resistance, with the voltage E minus V. So if you see, P is equal to I times of E minus V. This is the power dissipation in internal resistance. So your option is A. Question number 2. Light travels at a speed of 2.3 10 to the power 8 meter per second in water and 2 to the power 8 meter per second in glass. The refractive index of glass is 1.5. Which of the following expression can be used to determine the refractive index of water? So remember, if you are given speeds and refractive index of two different medium, we have a relation, and you can say that N1 V1 is equal to N2 V2. This is a general relation between refractive indexes and the velocities of two different media in which light is traveling, and one is showing that the light is coming from some medium, two is showing into the medium. So I am assuming that the light is coming from the water and entering into the glass, and we need, so that means this is my V1, this is V2 glass, and the refraction of the glass, so this is my N2, and I need to figure out refractive index of water, that means N1. So N1 into V1, V1 is 2.3 into 10 to the power 8 is equal to N2 is 1.5 into 2 into 10 to the power 8, and now N1 is equal to 1.5 into 2 times of 10 to the power 8 divided by 2.3 into 10 to the power 8. And now if you see, if you compare, so 2 to the power 8, 1.5, so your option is B. Question number 4. Ultraviolet light is incident on a metal surface and photoelectrons are released. The number of photoelectrons released per second is N, and the maximum kinetic energy of the released electron is Ek. Which of the following pairs of graphs shows how N and Ek vary with the intensity I of the incident light? Okay, so it's all about photoelectric effect and the relation of intensity of light with the kinetic energy and the number of electrons. So remember, intensity, if you increase the intensity I, this arrow I'm showing the just increasing. So if intensity is increased, then it will cause more electron to release. So number of electrons or emitted electron are going to increase, but there is no effect of intensity on kinetic energy, so Ek stays the same. It doesn't matter you use high intensity or low intensity, because in kinetic energy depends on frequency of the light, not the intensity. So intensity only cause increase in number of electron, but not the kinetic energy. So kinetic energy should be same. number of electrons should be increased if you are increasing the intensity. So if you see, you need to look for the graph in which kinetic energy is same or number of electrons are increasing. Clearly kinetic energy, number of electron constant here in this graph, so you cannot choose this. Number of electrons are increases, this is fine, but kinetic energy is also increasing, which is wrong in this option. And option B is number of electrons are increasing, kinetic energy, yes, this is the option. N are increasing with the intensities, but kinetic energy stays the same, so your option must be B. In B, just for your understanding, both are same, so this graph is correct, but this is wrong, so your option is B. Question number 5. Wire P and wire Q are connected in series across a battery. Wire P has a charge carrier density N and a diameter D. Wire Q has a charge carrier density 2N and a diameter 2D. The drift velocity of the charge carrier in wire P is V. Which of the following is the drift velocity of charge carrier in wire Q? A typical question of drift velocities, you will find many MCQs of same type. They are saying we have two wire, one wire is P and the other wire is Q, and they are connected in series, maybe directly or maybe with the help of some wire, it doesn't matter. So the second wire, and you can imagine that this is double the diameter, and of course, so but the charge carrier density here is 2N, here is N, diameter is D, diameter is 2D. So you need to figure out VQ, what is the drift velocity in VQ if this is the wire Q and this is the wire P, then the terminal velocity, oh sorry, not the terminal, sorry, this is drift velocity. Drift velocity is V for the wire P. Now if you see the relation, you have equation I is equal to N A Q V, where V is the drift velocity. So you rearrange for this equation for the drift velocity. So V is equal to I upon N A Q. Just for your understanding, I'm writing area in terms of formula. So you can say that I divided by N, A is pi r square, so pi r square, or you can say pi d square by 4, because r is d by 2, because in this given condition diameters are given. So I can write area is pi d square by 4 into Q. And now you can see that this is the drift velocity V, and the charge density N, and diameter is D. So I can say that this is the drift velocity for P. This is formula for the conductor P, because charge carrier density N and diameter is D. What if I say charge density is doubled? So first thing, wires, both of the wires are in series, so amount of current in both of the wire will stays the same. So for VQ, drift velocity in Q, you can say current stays the same, I, but charge density is double, 2N, pi stays the same, and diameter is also double, 2D, so it will become 2D square. So you can say 4D square by 4, and Q is also there. Clearly you can see 4 and this 2. If you multiply these, so you can say that I 4 times 8, 4 times 2 is 8 into N pi D square by 4 into Q, and this is V. That means VQ is equal to V by 8. So your option is A. Question number 6. Which of the following cannot be demonstrated in experiments using sound waves? A typical question of sound waves. Sound waves cannot be used for polarization. So sound waves can be diffracted, it can be refracted or superposed, but sound wave cannot be polarized, because for polarization we need a transverse wave, while sound waves are longitudinal or compressional waves. So option is B. Question number 7. Solar panels are devices that use sunlight as a source of energy to generate electricity. A solar panel has a surface area of 1.54 meters square. The intensity of radiation incident on the Earth's surface is 1050. The manufacturer states that the maximum output power of the solar panel is 250. Which of the following could be used to calculate maximum efficiency? Okay, so fine, this is efficiency. So the general concept of efficiency is output upon input. So efficiency E is equal to output power divided by input power, and you know that it's all about flux radiation falling upon an area, and flux radiation I is equal to power upon area, and remember this power is basically input power. So you can say that Pi is equal to I into A. That means 1050 multiplied by area, which is 1.54. So this is your input power, and manufacturer saying the output power is 250. Clearly efficiency is output power divided by input power. So you can see that yeah, this is your output PO and this is your input PI. So output upon input. So your option is D. Question number 8. Which of the following graph shows how power P dissipated by an ohmic conductor varies with the potential difference V across the conductor? Remember, I told you before, ohmic conductor resistance stays the same. There is no change in the resistance, and if you are varying potential difference, so we need to look at the equation in which we have a power dissipation related with V at constant R, which is P is equal to V square over R. Remember, power P is equal to VI. We cannot use this equation to see the effect of power due to change in voltage, because in this equation voltage and current both are changing. And this is the rule, if you are relating any two quantity from equation, the third quantity should be constant. Here R is constant, so we can relate P and V, and clearly we have a square, so we must have parabolic curve due to square. So P is relating with the square of the V, parabolic curve, and clearly option is D. Question number 9. Two waves from the same source travel along different paths and then meet at a point P. The phase difference between the waves at P is 1.5 pi radians. Which of the following is a possible path difference that could result in this phase difference being produced at P? Okay, it is a little tricky question. If you see the phase difference of 1.5 pi, so let's just draw some diagram to understand the situation. So if I say I have one wave, something like going something like this. So this is a wave number one, the red one, and I have another wave if I want to see the phase difference of 1.5. So if phase difference is 1 pi, that means the waves are at a difference of half of the wave, lambda by 2. That means the another wave will be starting, you know, from there, something like this, either go up or go down, it doesn't matter. So if waves are starting from here, then we have a phase difference of pi radian, half of the wave. But they are saying the phase difference is 1.5. That means the wave is starting from this position. So if you see the total length is lambda by 2, which is half of the wave, and then this additional length, so lambda by 4. So total path difference, if wave is starting from that point, so total path difference will be lambda by 2 plus lambda by 4. So total path difference is, you can add these two and you can say that the path difference will be 4 plus, so this is 2 plus 1 3 lambda by 4. So this is the path difference between the two wave if the wave is starting from this position, like going there, something like this. So the path difference is 3 lambda by 4, but this option is not given here. So we need to look at some other option. So the next possibility for 1.5 radian phase difference is the wave is starting from this position, either going up or coming down, it doesn't matter, but we need to see the just reference. So now how do you see the difference if the second wave is starting from that position? So this is 1 lambda, this is lambda by 2, and this is lambda by 4. So this is the total path difference. So you can say the total path difference is lambda by 2 plus, sorry, this is the first one is from here, this is lambda plus this one is lambda by 2 plus lambda by 4. So if you add these two, so at the end you have 4 plus 2 6 7 lambda by 4. That means this next option, if it is not 3 lambda by 4 for this phase difference, then there must be 7 lambda by 4 for the same phase difference of 1.5. So your option is B. This is the way that I think it's easy to visualize, but there is another method of looking at the the phase difference, but in my opinion it is the easiest one. So that's how we understand. Question number 10. When laser light is shown through a diffraction grating, a series of maxima is formed on a screen. Assuming all other factors remains constant, which of the following changes would increase the distance between adjacent maxima? Okay, decreasing the distance between the diffraction grating, decreasing the distance between the line of the diffraction grating, decreasing the intensity of the laser light. Clearly there is no relation of intensity intensity with the distance between the maxima, so of course we cannot waste time to think about that. Decreasing the wavelength of the laser light. Okay, now if you see for diffraction grating, we have equation that for maxima path difference should be equal to n lambda. It's a general concept for maxima. And for diffraction grating, this path difference is d sine theta is equal to n lambda. And they are saying between two adjacent maxima, so just I am assuming that this is the center of the screen O, and this is first order maxima, so n is equal to 1. Just to simplify my case, because I just need to see the distance between these two, which is, I'm calling it, let's say, delta x. So I need to relate this delta x when the delta x is going to change with any of these factor. So if you see the if we have two slits, something like this, and this is D, and you know that the light is coming from something like this, and if you see the diagram, this is the angle theta that we used here. So how much the distance or how far these maximas are depends on the value of theta. So if I say this is the position, the next maxima after O, now next maxima is there, so clearly if these lights go there, then angle of theta, value of theta is going to increase. So if you figure out theta, then definitely we can figure out, you know, the change in delta x. Clearly, if you need to find the relation of delta x, that means you need to find the relation of theta with other factor. So I'm rearranging this d sine theta equal to n lambda. So sine theta is equal to n lambda over d, and n is equal to 1. So sine theta is equal to lambda over d. Clearly you can say that the sine theta is directly proportional to the wavelength, and the sine theta is inversely proportional to the d, where d is grating element. D is grating element, this d. So clearly if lambda increase, wavelength increase, so theta must be increased. You can see if lambda increase, then theta increase, so the delta y or distance between the two maxima should be increased. So option D, decreasing the wavelength of the light. So of course we cannot have D's, but sine theta is inversely proportional to lambda. So if you decrease the distance between the two lines, so the value of sine theta is going to increase because of increase in theta. So the distance, decreasing distance between the lines of diffraction grating is your option. I explain again. See, instead of at that position, if the light is coming, the next maxima is reaching there, then you can clearly see that. So theta will be more, so delta x will be more. So if delta x increase, then theta increase. So measuring theta means we are measuring the vertical distance. So option is B. Question number 11. The diagram shows some of the energy levels from an atom of hydrogen. These are energy levels. Determine the transition between energy levels that would result in the release of a photon with the frequency of this. So we need to find which transition between any of these two levels gives us a photon of that frequency. So the easiest way is, first we figure out energy associated with this photon, and then we can figure out which two level, which energy difference of the two level giving us that amount of energy. So let's find out the energy of the photon. So E is equal to HF. H is a Planck's constant. If you see your data sheet, which is 6.63 into 10 to the power minus 34 joule second times frequency 7.48 into 10 to the power 13 hertz. So energy associated with that photon will be 4.95 into 10 to the power minus 20, but this is in joule. But if you see the diagram, we are given energies in electron volt, so we divide this energy in joule with electron charge. So in electron volt, you see that E is equal to 4.95 into 10 to the power minus 20 divided by charge of electron 1.6 into 10 to the power minus 19, and then the energy will be equal to 0.31 electron volt. Now it's easy to work with that. You need to keep subtracting any two of the level to figure out which difference is equal to minus 0.31. Clearly, if you see a quick 13.6, 3.4, these two. So if you see 0.85, I'm not considering for the meantime these negative. Sometimes it gets confused. So 0.85 minus 0.54. It will give you 0.31 in terms of magnitude electron volt. So that means electron electron can emit a photon of that energy or absorb that photon. So we need to see whether the electron is coming from 0.54 to 0.85 or 0.85 to 0.54. So you see, they are saying that which level would result in release of a photon. That means electron is being released, and it is only possible if electron jumps from higher energy level to the lower energy level, then it will release the photon of that energy. That means electron is the transition of the electron is from minus 0.54 electron volt to minus 0.85 electron volt. A student is reading about the wave nature of electrons. He writes a statement about wave particle duality. If every particle has a de Broglie wavelength, it should be possible for a moving car to have the same de Broglie wavelength as a fast moving electron. Although the car would be moving very slowly, determine whether the student's statement about the speed of the car is mathematically correct. The speed of the electron is given, mass of the car is 900 kilograms. So in fact, we need to figure out velocity of the car, VC, whether it is in accord with the statement with the student's statement. So it's all about de Broglie wavelength, or wavelength associated with the moving particle, and you know that the de Broglie wavelength lambda in generally is h upon mv. So I say that for electron, wavelength is lambda e, h is Planck's constant, it doesn't matter. So mass of electron divided by velocity of electron. And for car, I can write the wavelength of the car, lambda c, is equal to h upon mass of the car divided by velocity of the car. And now that they are saying that the car has the same de Broglie wavelength as that of the fast moving electron, that means lambda c is equal to lambda e. That means h upon mc vc must be equal to h upon MEVE. So now we can figure out HH gets cancelled, so we need to find VC, so we can make VC as a subject. So VC would be equal to MEVE divided by MC. So now you can substitute all the numbers. ME is the mass of electron. So from your data sheet, you can find mass of electron, which is 9.11 into 10 to the power minus 31 kilogram. Minus 31, this is minus 31. Times of velocity of electron, which is 1.5 into 10 to the power 7, divided by mass of the car, which is 900. And if you solve this, the velocity of the car will be equal to 1.52 into 10 to the power minus 26 meter second inverse. And clearly, indeed, the velocity of the car is very small, or very is moving very slowly. It's 10 to the power minus 26. So of course the statement is correct. So you need to write the statement that the velocity of the car is really small, so statement is correct. Suggest why the de Broglie wavelength is not a useful property for a car. Okay, the reason why it is not useful for the car, because car has a very heavy mass, and of course it has a very due to high mass it is not behaving as a wave because of small velocity, high mass, so wavelength associated with very small, so it is not behaving as a wave. Question number 13. The photograph shows an electric skateboard. On particular type of electric skateboard, use an electric motor connected to a 22-volt rechargeable lithium-ion battery. A fully charged battery is able to pass 3600 coulomb of charge through the circuit and will allow continuous operation for the skateboard for 40 minutes. Calculate the total energy stored in a fully charged lithium-ion battery. So you need to find energy stored. In electricity, energy stored is equal to VIT. This is the formula that we know, but we don't have current, so we can say that V is equal to I is charge upon time into T. That means T gone, so E is equal to VQ. Just multiply voltage with the amount of charge. So voltage is 22 and charge is 36,000. So energy stored in the battery is 7.92 into 10 to the power (5) joule. This is the amount of energy. The electric skateboard travels at the speed of 16 km per hour. Calculate the time taken for the electric skateboard to travel 2 meters. So we are given a distance, we need to find the time. Speed is given, so first we know that we need to find time. So first we convert this kilometer per hour into meter per second. And how do we do that? So velocity is 16 km per hour multiplied by 1000 divided by 3600, then it will give you 4.4 meter per second. And now you need to find time, so time is equal to distance divided by speed, which is V, and then distance is 2 divided by 4.4, so time is 0.45 second. That's how you can figure out the time for the 2 meter. While the electric skateboard is in use, the battery provides a constant current. Calculate the number of electrons that flows past a point in the circuit during the time for electric skateboard to travel 2 meter. So first we find how much current is there. So the total current is I is equal to Q by T, and the total charge is 36,000 divided by the total time, which is 40 minutes times 60 in second. So you can say that the total current is 15 ampere that is flowing through the circuit. And now for how much charge is flowing for that time? Now we need to find the amount of charge for this small time for 2 meter distance. So you know that the Q is equal to, or Q dash, because Q I have already said the total charge. So Q dash, the new amount of charge for 0.45 seconds. So Q is equal to IT That means you say 15 times of time, which is 0.45. That means this is 6.75 coulomb. This is the amount of charge flowing in 0.45 second. And how many electrons? So you divide this amount of charge, this amount of charge with the charge of one electron. So you say that so number of electron n is 6.75 divided by charge of electron, which is 1.6 into 10 to the power minus 19. And this is general approach. If you have amount of charge, you divide it with the charge of electron, then you can have number of electrons. So n is equal to 6.75 divided by this. So n will give you 4.23 into 10 to the power it is 4.2 is 19 electrons. These many electrons are flowing in 0.45 second and during a distance of 2 meters. Thank you very much for this video. Have a nice time.